Hello students, welcome to the class. So in the previous class we had discussed the last part. What we had discussed was Bohr's model of an atom, and we had discussed some of the postulates, yes, regarding the Bohr's model. Neil Bohr, what he did, he just slightly modified Rutherford's model. He came over certain outcomes of the Rutherford and he proposed the model. Yes. So according to his model, what he said, the atom is made up of what he said, the atom, it is made up of, it is having a small body at the center of the atom, and that small body is called nucleus, and it is containing the positive charge. An atom consists of the small heavy positively charged nucleus in the center, and electrons revolve around the atom, right? These electrons revolve around the atom, just like a assumption of Rutherford. Yes. Further, what he said, the electrons revolve around the nucleus in certain permitted circular orbits. You can see here these permitted circular orbits, they are called orbits or they are called shells. They are called shells. Okay. The which orbits are allowed for the electrons? Can I place any electron in any orbit? No. Only those orbits are allowed, or you can say only those orbits are permitted whose angular momentum mvr is equal to is the integral multiple of h upon 2 pi, where n is the number, principal quantum number. It depends on, it tells us about the shells. Okay. Only when this is obeyed, that electron will be allowed in that particular orbit. Yes, and this is the orbit number. Further, what he said, until and unless the electron is revolving in its own orbit, until and unless it is revolving in its own orbit, it will neither lose energy nor it will gain energy. So it will neither lose energy nor gain energy. So energy for a particular orbit, energy of the electron for a particular orbit remains fixed. Therefore, the orbits are also called as energy levels. Every orbit is associated with certain energy, and that energy remains fixed. Since the energy remains fixed, it is also called as stationary states. The orbits are also called as stationary states, and these energy levels, they are denoted by principal quantum number. I'll tell you what is principal quantum number. Right now you understand it is denoted by n, where n stands for 1 2 3 4. The shell nearest to the nucleus is numbered 1, and as you move away from the nucleus, we go on numbering. Yes, 1 2 3 4 and so on. Or n is equal to 1 shell is denoted by symbol k, 2 shell by l, symbol m for third shell, n for fourth shell, and so on. Yes, so this is positively charged nucleus, and we have k, l, m, n shells. Okay. Further, what he said, when an electron in a particular orbit is present, it's for this electron, this is the orbit or energy level, let me say. So for that electron, that orbit becomes the ground state. Yes. When that electron somehow gains the energy, it will absorb energy, and it will jump to higher energy level, from lower energy level to higher energy level. And this is called excitation. It is called excitation. And the higher energy state is called excited state, where the electron will be unstable. Therefore, what the electron does, it will try to come back to its normal ground state by emitting the energy, emitting the radiation. So when the electron jumps from higher energy level to lower energy level, it is called what? It is called transition. It is called transition. Yes. And when transition is occurring, there is radiant energy which is emitted. There is radiant energy which is emitted. Yes. So this is all about Bohr's model. So you can see here. So electrons revolve around the nucleus in definite energy levels called orbits or shells in an atom without radiating energy. As long as the electron remains in a shell, it never gains or loses energy. The gain or loss of the energy occurs within the orbit only due to jumping of the electrons, from one level to another. Yes, when it jumps from lower energy to higher energy, it gains energy, plus h nu, gaining of energy. Higher energy to lower energy, it is giving out energy, h nu. Yes, yes, it is giving out energy. The angular momentum mvr of an electron is equal to nh upon 2 pi. The angular momentum of an orbit depends on what? Depends on the quantum number n, and it is integral multiple factor of h upon 2 pi. We have seen this. Bohr suggested circular orbits of electrons around the nucleus of the hydrogen atom, but later it was proved that motion of electrons is not in a single plane, but it takes place in 3 dimensions. So this was being, so here what you see, the first one, this was being suggested by Bohr. That is, electrons are revolving in a circular orbits. But later, with certain further studies, it proved that they are not in one plane. See, this is one plane, this is another plane, this is another plane, three-dimensional plane that is taken. So in the three-dimensional space, the electrons are found, probability of the electrons is being found. So this led to the explanation of next concept. Yes. So here they have clubbed them. So in atom, electrons, I'm repeating again, that's it. So you can see all the points I have included. Only those orbits are permitted. We have seen all of them. Last point, when energy is supplied to an electron, it absorbs the energy and in fixed amounts as quanta and jumps to higher energy level. And the excited state is unstable. We have seen the electron may jump back to the lower energy state, and in doing so it emits same amount of energy, and that is given by delta E is equal to E2 minus E1. Whatever energy is present in second energy level minus when it gives out that limited energy which it has acquired, minus E1, will get delta E, change in the energy. This is explanation for Bohr's postulates. See, when electron jumps from higher energy level to lower energy level, what happens? So here, these are orbits or energy levels. When you move from the nucleus, energy of the orbits increases. So here, if there is some energy E1, this will be energy E2, this will be energy E3. E3 will be more than E2, will be more than E1, like this. Energy of the orbits goes on increasing. And when electron jumps from higher energy level or excited state to lower energy level or ground state, there is emission of the radiation. Yes, emission of the radiation, and that is emitted in the form of photon with E is equal to h nu. E is equal to h nu. Correct? Okay. What are the achievements of Bohr's theory then? Bohr's theory has explained the stability of the atom very well. Yes, it has explained the stability of atom. Bohr's theory has helped in calculating the energy of the electron in hydrogen atom and one electron species. It might be hydrogen with one electron or hydrogen like ions. Hydrogen like ions. What are hydrogen like ions? Helium plus is an ion. It is hydrogen like ion because it is also having one electron. See, helium has two electrons. When I write He plus, it becomes one electron. Lithium plus 2. Lithium has got how many electrons? Lithium has got 3 electrons. So Li plus 2 becomes how much? 1 electron. So such species, such ions are called hydrogen-like ions. And Bohr's theory was successful in explaining about hydrogen-like ions also. The mathematical expression for energy was derived. Mathematical expression for even for velocity and all were derived. So for energy, the expression is minus 2 pi r square mass of the electron e square e raised to 4 z square upon n square r square, where m is mass of the electron, e stands for charge of the electron, r stands for Rydberg constant, and z stands for the atomic number. And the value of it comes out to, when you substitute all the constant things, z only is not constant and n is not constant because n varies as the number of orbits vary, and z is what? Atomic number. It varies for different atoms. If it is hydrogen, it is 1. Yes, so the value comes out to these values. It comes out to these values. Bohr's theory has explained atomic spectra of hydrogen atom. It has explained the atomic spectra of hydrogen atom. Then why Bohr's theory failed? Limitations of Bohr's theory. The theory could not explain the atomic spectra of atoms containing more than one electron. Multi-electron system was not explained by Bohr's theory. Only one electron, that is hydrogen and hydrogen-like ions, was explained. Bohr's theory failed to explain the fine structure of spectral lines. When spectral lines were further viewed in a broad manner, there were still fine lines. That was not explained. Bohr's theory could not satisfactorily explain Zeeman effect and Stark effect. In presence of electric field and in presence of magnetic field, there was splitting of the lines. What spectral lines we have seen, no? Lyman series, Balmer series, all those lines were splitting up. And Bohr's theory, that was called Zeeman effect and Stark effect. That was not being explained by Bohr's theory. Bohr's theory failed to explain the ability of the molecules, atoms to form molecules by chemical bonds. How the atoms are combining to form a molecule was not being explained by Bohr's theory. And it was not in accordance with Heisenberg's uncertainty principle. Now you may say, what is that? Yes, Bohr through his theory, what he gave was, he gave the exact position of the electron by measuring the radius. By measuring the radius of the orbit, he gave the exact position of the electron. And by measuring the velocity, he gave the momentum of the electron. And we know that momentum is equal to v is equal to mv, so by measuring the velocity he gave the momentum, yes, which is not possible according to Heisenberg's uncertainty principle. So this was not in accordance with Heisenberg's uncertainty principle. Then what is Heisenberg's uncertainty principle? Before that, we have some questions here. How do electrons move in Bohr's model? What he said, the theory notes that electrons in atoms travel around the central nucleus in circular orbits. He said it move in circular orbits and can only orbit stably at distinct sets of distances, that is radius is there, from the nucleus in fixed circular orbits. Such orbits are related to certain energies and are also referred to as energy shells or energy levels. How did Bohr discover electrons? Bohr was the first to discover that electrons move around the nucleus in different orbits. Rutherford said what? Electrons are revolving in certain paths called orbits. But there is only one orbit, or there are many orbits, or there are different orbits, was being found by Bohr. Yes. Did Bohr model have neutrons? The nucleus in the atom's Bohr model holds most of the atomic mass in its protons and neutrons. The negatively charged electrons, which contribute little in terms of mass but are electrically equivalent to protons in nucleus, orbit the positively charged core. Yes, it has. How did Sommerfeld modify Bohr's theory? After Bohr theory, Sommerfeld's theory came. Bohr-Sommerfeld theory it was called. What Sommerfeld scientist did, he just modified slightly Bohr's theory. What he did? Many modifications have been introduced to the Bohr's model, most notably the Sommerfeld model or Bohr-Sommerfeld model, which suggested that electrons move around a nucleus in elliptical orbits rather than circular orbits of the Bohr's model. So Bohr's model says they are moving. So Bohr's model says they are moving around the nucleus in circular orbit. Yes, Bohr's model says. And Bohr-Sommerfeld model says they are not moving in circular orbits. They are moving in elliptical manner. They are moving in elliptical manner. Elliptical manner, yes. So this was being said by Bohr-Sommerfeld theory. Yes, so that was the modification done by him. Next, so dual behavior of matter. De Broglie, what he said, he suggested that De Broglie in the year 1924 proposed that the matter, like how matter has double behavior, radiations also show dual nature. Yes, both particle like and well as wave like properties. This means that like photons, electrons also have momentum as well as wavelength. So what did De Broglie do is he derived the equation. De Broglie derived the equation which was called for the wavelength of the electrons. For the wavelength of the electrons. So what he did was he used very nicely the French scientist. He was a French physicist. I'm sorry. He suggested that if light has both particle and wave-like nature, then Similarly, it should show duality in nature. Electron also behaves like material particle as well as wave. So this presented a new wave mechanical theory of matter. According to this dual nature of electron, that is dual nature of matter presented by De Broglie, small particles like electrons, when in motion, possess wave properties. So according to De Broglie, the wavelength associated with a particle of mass m moving with velocity v is given by the relation lambda is equal to h upon mv, where h is Planck's constant. And what is m into v? Mass into velocity is nothing but acceleration. Therefore, I can write h upon p. I can represent it as h upon p. Yes, we can represent it as h upon p. So how this relation altogether came, I can show you all here. Yes. So we know that According to Planck's equation, E is equal to h nu, or I can also write it as E is equal to h c by lambda. Call this as equation 1. And according to energy of photon on the basis of Einstein's mass energy relation, I know that E is equal to mc square. Call this as equation 2. When things are equal to same things, they are equal to one another. So I can write hc by lambda is equal to mc square. C gets cancelled. So I want equation for lambda. So I will take lambda here. Lambda is equal to h by mc. What is c? C is velocity of light. But here I am talking about particle. So instead of c, which is velocity of light, here since I am talking about particle, I can replace c by v, general velocity term. Yes. So I will write it as lambda is equal to h upon mv. And I know that m into v is nothing but p. That is what? Momentum. That is momentum, right? So lambda is equal to h by p. This two equations, equation 3 and equation 4, they are called de Broglie equations. They are called de Broglie equations. Yes, so they are called de Broglie equation. So this de Broglie equation, it is applicable to all the material objects, but it has significance only in case of microscopic particles. Microscopic particles. The particles are microscopic. So since we come across macroscopic objects in our everyday life, de Broglie relationship has no significance in everyday life. Again, this theory failed. Since we come across macroscopic particles, right? So de Broglie's equation doesn't have any significance in our daily life. Yes, so this is according to de Broglie. So when an electron is possessing wavelength, it will be moving around the new. See, according to all the theories what we saw till now, the electron is revolving. One of them said, Bohr said they are revolving in the circular path. Then Bohr-Sommerfeld theory said they are revolving in the elliptical path. Yes, these electrons I'm speaking. Electrons are revolving in circular path. Here electrons are revolving in elliptical path, they said. Actually, they are revolving how? They are revolving in the form of wave. You can see here. Crest, trough, crest, trough. So they are revolving in the form of wave. So this is first energy level, second energy level, third energy level, fourth energy. So they are revolving in the form of wave. So only they are possessing some wavelength. So only they are possessing some wavelength. So lambda stands for wavelength. Planck's constant 6.626 into 10 raised to the minus 34 joules second. Momentum, mass of the particle, velocity or speed of the particle. Yes? Okay. So Heisenberg's uncertainty principle. Now what does Heisenberg's uncertainty principle says? The principle says that it is impossible to determine simultaneously the exact position and momentum, that is velocity of an electron. Simultaneously, you cannot determine both exact position and momentum. So only we say Bohr's model is not in accordance with Heisenberg. What Bohr said, he calculated the radius of the orbit. Yes, he calculated the radius of the electron. I'll show you what radius of the stationary states he calculated. Nth orbit, he gave it as a naught upon z. That is nothing but 52.9 n square, a naught n square upon z picometers. This was the radius given. So with this radius, what we say, we can say exactly the first orbit is how far, and electron is there in the first orbit. So he gave, with the radius, he gave the position, exact position of the electron. And even he gave the term for velocity of the electron. He gave 2.188 into 10 raised to 6 into z, that is atomic number, upon n. Meters per second. So he gave the velocity with what velocity the electron is revolving in its orbit. Even he gave the energy, we have seen energy of the electron in nth orbit. He gave it as minus RH z square by n square. Yes, these were all being given by Bohr. So it's only, but what Heisenberg's uncertainty principle says, it is impossible to determine. If you are determining exact position of the electron, you will go wrong with the velocity. If you are trying to determine exact velocity, that is momentum of the electron, you will go wrong with the position. Both of them cannot be found exactly at the same time. And he gave a mathematical expression wherein he mentioned delta x into delta p is more than or equal to h upon 4 pi. H upon 4 pi. What is delta x? It is uncertainty in position. Some error will occur. Delta p is uncertainty in momentum, is more than or equal to. When you're solving numericals, you can take it as equal to h upon 4 pi. The more accurately you know the position, the less accurately you will know the momentum. Yes, if the uncertainty in position is less, that means you are knowing the position more accurately. If the uncertainty in position momentum is less, that means you are knowing the velocity of the electron in a better way, and vice versa. So this is Heisenberg's uncertainty principle. So it was not, Bohr's postulate was not in accordance with Heisenberg's uncertainty principle. Even you can write it in another form also. Delta x into, what is delta p? It is momentum, and we know that p is equal to mv. So I can write m delta v. I'm not writing delta m delta v because mass doesn't change, velocity changes. So delta x into m delta v is greater than or equal to h upon 4 pi. It can be written like this. Or delta x into delta m is greater than or equal to h upon 4 pi m. I can write it like this also. Yes. So this is Heisenberg's uncertainty principle. It is impossible to determine simultaneously the exact position and exact momentum of an electron. The more accurately you know the position, the less accurately you will know the velocity, that is momentum. Here it is there. So delta x into delta p is greater than or equal to h upon 4 pi. Delta p is nothing but change in momentum and uncertainty in momentum, which can be written as m delta v. I cannot use here delta m because mass does not change. Yes, velocity may change. There might be error in the velocity, but not in error in the mass. If I say there is an electron which I have taken, the position of the electron in the orbit may change. The velocity of the electron in the orbit may change. But will the mass of the electron change? It will be 9.1 into 10 raised to minus 31 kg only. Yes. Delta V, or I can write it in this form also, finding delta V greater than or equal to h upon 4 pi m delta x. Or I can find delta x also, h upon 4 pi m delta V. Yes, substitute all the values, you will get delta V, which might be more than or equal to 2.189 into 10 raised to 8 meters per second. So this is Heisenberg's uncertainty principle. So what is the significance of Heisenberg's uncertainty principle? It rules out the existence of definite paths. So till now we say that electrons are revolving in definite paths. But uncertainty principle says that there is no definite path for the electrons. Might be there might be orbits, but orbits are not the definite paths. Or you can say the trajectories of the electrons or other similar particles. That is the significance. The effect of Heisenberg's uncertainty principle is significant only for, again, microscopic objects and doesn't work good with macroscopic objects, same as de Broglie's wavelength expression and mathematical expression. It is being shown here, where delta x is uncertainty in position, delta p is uncertainty in momentum. If it is delta v, it is uncertainty in velocity, and h is Planck's constant, m is mass of the particle. Reasons for the failure of Bohr's model. With these reasons only, we'll proceed further. The wave character of the electron is not considered in Bohr's model. Bohr did not consider. Who said it? It was said by de Broglie. Electrons are evolving in the form of waves. According to Bohr's model, an orbit is clearly defined path, and this path can completely be defined only if both position and velocity of the electrons are known exactly. Therefore, it is not correct in case of Heisenberg's uncertainty principle. Therefore, that was another reason for the failure. So now, with all these failures, starting with Thomson's atomic model, then Rutherford's gold foil experiment, nuclear model of an atom, then the electromagnetic wave theory, Maxwell's wave theory, then the Bohr's atomic model, and then Sommerfeld-Bohr's atomic model. Then we came across de Broglie's wave equation, Heisenberg's uncertainty principle. All these were not accepted. Therefore came the Schrodinger's wave equation. Yes, Schrodinger, he is known as the king of classical mechanics. Yes, so he proposed a equation, Schrodinger wave equation. It is a mathematical expression describing energy and position of the electron in space and time, taking into account the matter wave nature of the electron inside an atom. It is based on three considerations: classical plane wave equation, de Broglie's hypothesis of matter and wave, conservation of energy. What did Schrodinger do? Schrodinger equation gives us detailed account of form of waves, functions, and probability waves that control the motion of some smaller particles. The equation also describes how these waves are influenced by external factors. Moreover, the equation makes use of energy conservation concepts that offers details about the behavior of an electron that is attached to the nucleus. Besides, by calculating Schrodinger equation, we obtain psi, PSI, it is pronounced as psi, and psi square, which helps us to determine the quantum numbers as well as the orientations and shapes of the orbitals where electrons are found in a molecule or an atom. This is all the story of Schrodinger's wave equation. Let me tell you what actually is this Schrodinger's wave equation. This is Schrodinger's wave equation. Schrodinger's wave equation. So it comes under quantum mechanical model of an atom. So it is quantum mechanics. It is a theory that deals with the study of motion of microscopic objects which have both particle and wave-like property. The fundamental equation of this quantum mechanics was developed by Schrodinger. This equation describes a function. This equation, what you are seeing, mathematical expression, it describes a function called psi. It is pronounced as psi. Electron wave function it is. What it is? It is a wave function. It is a wave function. This wave function stores all information about the electron like energy, position, orbital, etc. As such, what you are seeing this psi, it doesn't have any significance. Then you may say, what is the need to study? When you square this psi, it becomes a psi square. This is significant. This is significant. The information stored in psi about the electron, you can just extract the information. Understanding? Okay. So before going very depth, let me start with what is this actually Schrodinger's wave equation. Schrodinger wave equation, the mathematical expression what you're seeing is Schrodinger wave equation. It was developed by Schrodinger in 1926. In it, electron is described as a three-dimensional wave in the electric field of positively charged nucleus. What mistakes so far we have discussed about Thomson's model, Rutherford's model, Bohr's model, electromagnetic wave theory, then de Broglie's model, Sommerfeld's Bohr model, and even Heisenberg's uncertainty. So many models we have seen, but all of them failed. The reason was everybody were trying to give the exact information about the electron, exact position, say. Exact position they were trying to give. That electron is present here only. Now, if see, so for example, you are present in your house. If someone from outside asks, where are you? And the person who is there in the house, he says, just climb 10, go 10 steps forward, take a left turn, then climb 10 steps upward, take a right turn, then take a left turn, open the door. Can that person reach the reach your destiny where you are present? Absolutely not, because for him the 10 steps are different and for you the 10 steps are different, right? You know actually where you are. Your relative knows where you are. Understanding? So all these people, what they did were, they were trying to give the exact position for the electron, so they failed. What this quantum mechanics did was, or you can say this person, the king, this equation is called the king of all quantum mechanics. Yes, what this person did was, he did not try to give the exact position. He gave the probability. He gave the possibility of finding the electron in an atom. The probability of finding the electron. He mentioned there is certain region in an atom, and he mentioned that there is So if this is an atom, yes, so he mentioned there is certain region in an atom where the probability of finding the electron is maximum, where the possibility of finding the electron is maximum. So that certain region, it was used by this particular thing. Psi is wave function, which tells us about the amplitude of the wave. That's it, amplitude of the wave. That is psi. But what is psi square? Psi square is called probability density. It is called probability density. Remember, psi is not having any physical significance, but psi square is very significant. What is psi square? It is probability density. So what is probability density? Probability density is the probability of finding the electron at a point within an atom which is maximum. If psi square is maximum, then most of the time the electron is found there. And that particular region in the atom is called orbital. That particular region in the atom is called orbital. And there is some region in the atom, where psi square is 0. That means what? The probability of finding an electron is absolutely nil. It is 0. And that particular region in the atom is called node. It is called node. Understanding? So this expression gives us the entire information of electron in an atom. What information? You can say it gives us the entire address of electron in an atom. Address means the position, the energy, velocity, everything. It gives about the electron. So they did not try to give exact position. They said in an atom there is a three-dimensional space, not two-dimensional. There is a three-dimensional space where probability of finding the electron is maximum, and that is denoted by psi square, which is probability density. So if psi square is maximum, it means what? The probability of finding the electron is maximum there, and that is called orbital. It is called orbital. And there is some region in the space where probability of finding the electron is absolutely 0. That means psi square is 0, and that region is called nodes. It is called nodes. So the probability of finding an electron at any point around the nucleus can be determined by the help of this Schrodinger's wave equation. How do we pronounce it? This symbol is pronounced as dou. Dou square psi upon, this is psi, dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m upon h square e minus v psi is equal to 0. So this Schrodinger wave equation gives us the complete address of the electrons. And when you solve this Schrodinger's wave equation, you will get three solutions in the form of three numbers, and those three solutions were called quantum numbers. Quantum numbers. Now you may say, teacher, we have heard that there are four quantum numbers. The solutions of Schrodinger's wave equation gave us only three quantum numbers, and one more is from the electrons. It's from the electrons separate study. We will discuss what are those quantum numbers. Understanding? So this is Schrodinger's wave equation. It is written like this also. H psi is equal to E psi, where H cap is Hamiltonian operator. This is wave function, and E is energy. E is the energy. So just now we said atomic orbital. So what is, so physical, before that, physical significance of psi and psi square. Psi is what? Wave function. It represents only the amplitude of the electron wave. Yes, it represents only the amplitude. For a single particle, the square of wave function is what? Psi square. It is proportional to the probability of finding the particle in that region. Psi square is maximum, means what? The probability of finding the electron is maximum around the nucleus, and the place where the probability of finding the electron is maximum is called electron density. The place where probability of finding the electron is maximum is called electron density, or it is called electron cloud, or it is called atomic orbital. It is called atomic orbital. Okay, so the solution of Schrodinger's wave equation, it provided us a set of quantum numbers, and those quantum numbers, say, what is the use of those quantum numbers? They describe us the definite energy the state of the electron in an atom, and information about the shapes and orientations of the electrons around the nucleus. Around the nucleus. Yes. Okay. So atomic orbitals, which is also called electron density or electron cloud. So atomic orbitals are the mathematical functions that provide insight into the wave function of the electrons that exist around the nuclei of the atoms. In the fields of quantum mechanics and atomic theory, these mathematical functions are employed in order to determine probability of finding an electron in a specific region. Note that the term atomic orbital can be used to refer to the physical space or physical region around an atom's nucleus in which the probability of finding the electron being present is maximum. So for this, psi square is maximum. Then we call it as atomic orbital in a three-dimensional space. Yes. Then what are nodes? Node is a point where the probability of finding an electron is 0. So psi square is 0. Probability density is 0. Then that region is called node. And for a given orbital, there are two types of nodes. One is radial node and another one is angular node. Radial node is also called as nodal region. Circular. Radial nodes. Spherical surface where probability of finding an electron is 0. The number of radial nodes increases with principal quantum number n. Angular nodes. Angular node is also called nodal plane. It will be in the form of plane. It is plane that passes through the nucleus. Angular node is equal to azimuthal quantum number L. So number of radial nodes is n minus L minus 1. L minus 1. And number of angular nodes is L. Total number of nodes will be n minus 1. If they give certain quantum number, then you can calculate the number of radial nodes, number of angular nodes, and from that you can calculate the total number of nodes. Total number of nodes. Here is the picture. Yes, can you see here? I've taken first 1s orbital. Here there is no node. There is no node. Yes, n minus 1. So 1 minus 1 is 0. There is no node. 2s orbital. 2 is the quantum number. N is equal to 2 here. So white portion what you are seeing, that is the node. So 2 minus 1, that is equal to 1. So there is one radial node. And what about angular node? For s orbital, L is 0. So how many angular nodes? There are no angular nodes. 3s orbital. Can you see here? White part here, white part here. So n is equal to 3. So 3 minus 1 is 2. So there are 2 radial nodes. And L is equal to 0. So there are no angular nodes. And it is shown, same is shown here. 1s, no nodes. 2s, white part is a node. And remaining part what you are seeing, it is orbital. It is orbital. Yes, so this is the images of nodes and orbitals. Quantum mechanical model of an atom. So quantum mechanics is a theoretical science that deals with the study of motions of microscopic objects that have both wave-like and particle-like properties. What are the important features? We have seen just now everything. This Schrodinger's wave equation comes into this context. Energy of electrons in atom is quantized. Existence of quantized energy levels is a direct result of wave-like properties of the electrons. Both exact position and velocity of an electron in an atom cannot be determined simultaneously. An atomic orbital has a wave function psi and it is not significant. Probability of finding the electron at a point within an atom is proportional to the square of the orbital wave function. Psi square. Square of the orbital wave function, that is psi square. And that is known as what? Probability density. It is always positive. From the values of psi square at two different points within atom, it is possible to predict the region around the nucleus where electron most probably will be found. Yes, Bohr's model is this. This is actually Bohr-Sommerfeld model. And here this side you can see quantum mechanical model. They have not given any particular paths for the electrons. The blue things are the electrons. The yellow things, what you are seeing, they are the neutrons. And the red things are protons, right? Quantum numbers. So from where we get these quantum numbers? Quantum numbers, we get them as the solutions When Schrodinger's wave equation is solved, we get three solutions, and those three solutions are nothing but quantum numbers. They are quantum numbers. So atomic orbitals can be specified by giving their corresponding energies and angular momentums which are quantized. That is what? They have specific values. The quantized values can be expressed in terms of quantum numbers. These are used to get complete information about the electron. A particular quantum number tells us about particular information. Like we have first quantum number, that is principal quantum number, denoted by small n. It tells us about the energy. Azimuthal quantum number we have, denoted by small l. It tells us about the shapes of the orbitals. Then we have magnetic quantum numbers, denoted by m. It tells us about the orientation. So these three are obtained from Schrodinger. Fourth one is spin quantum number, denoted as s. Spin of the electrons are being told. Yes, okay. Principal quantum number. Principal quantum number, it was being proposed by Bohr, Niels Bohr, and denoted by n. So what does it says? It determines the average distance between the electron and the nucleus. Means what? It denotes the size of the atom. It is most important quantum number since it tells the principal energy levels or shells to which the electron belongs. It is denoted by the letter m, n, I'm sorry, small n, and can have integral multiple values except 0. There cannot be energy level with 0 number, right? So n is equal to 1, 2, 3, 4, and so on. The various principal energy cells are also designated by the letters K, L, M, and N shells, starting from their nucleus. Principal quantum number gives us the following information. It gives us average distance of the electron from the nucleus. Very important, it determines the energy of the electron in the orbit where electron is present. See, even you can find the maximum number of electrons in an orbit using a principal quantum number. Using principal quantum number n, the maximum number of electrons in an orbit can be found. For a particular orbit, how many electrons can be present? It is given by 2n square, where n stands for principal quantum number. Yes, no energy shell in an atom of known elements possesses more than 32 electrons. Maximum number of electrons are 32. So let us see. If n is equal to 1, we call it as K shell. Yes, so 2 into 1 square, 2 electrons. So first shell has got 2 electrons. N is equal to 2, L shell. So 2 into 2 square, 8 electrons. N is equal to 3, M shell. 2 into 3 square, 3 3s are 9, 18 electrons. N is equal to 4, N shell. 2 into 4 square, 4 4s are 16, 16 2s are 32. This is maximum. No energy shell, no orbit of known elements possess more than 32 electrons. So it gives information about all these shells. Yes. Even angular momentum can be calculated using this only. No. Yes. NH upon 2 pi, yes or no? So it can be calculated using the same quantum number, right? So this is about principal quantum number. See, this is n equal to 1, first shell, E2n square, 2 electrons, n equal to 2, L shell, 8 electrons, n equal to 3, M shell, 18 electrons, 4, 32 electrons. Then again 18, 18, 2. So it goes on changing. Maximum is 32 electrons only. Coming to the second one, azimuthal quantum number, which is denoted by the symbol small l, n, L. It is found that spectra of elements contain not only main lines, but there are some fine lines also, which was not explained by Bohr. This number helps us to explain the fine lines of the spectrum. So what information azimuthal quantum number gives? It gives us about the number of subshells. In a shell, there are subshells. Yes, in the main shell, there are subshells. That information is being given by azimuthal quantum number. The angular momentum of the electron present in any subshell. relative energies of various subshells, and shapes of various subshells. This quantum number, see, azimuthal quantum number is dependent on principal quantum number. Yes. So azimuthal quantum number for a given value of n, it can have any values ranging from, if for a given value of n, L can have any values ranging from 0 to n minus 1. Like for example, if n is equal to 1, n cannot be 0. Yes, if n is equal to 1, then L will be from 0 to n minus 1. So 0, n minus 1, 1 minus 1 is 0. So L will be 0. And this particular subshell is called S. If n is equal to 2, L values vary from 0 to 2 minus 1. So it is 0 and 1, correct? If it is 0, it is yes. If it is 1, we call it as P. N is equal to 3, L value 0 to 3 minus 1. So 0, 1, 2. For yes, it is 0, it is called yes. For L is equal to 1, it is called P, and this is D. N is equal to 4, L values vary from 0, 1, 2, and 3. So for 0, it is S, P, D, F. These are the subshells. So what is the value of azimuthal quantum number for S subshell? 0. L is equal to 1, P subshell. L is equal to 2, D subshell. L is equal to 3, F subshell. Understanding? So see, values of L equal to 0, 1, 2, 3, 4, and so on. Notations. For 0, it is yes. For 1, it is P. For 2, it is D. For 3, it is F. 4, it is G. 5, it is H. Like this. Understanding? So values of N vary from 0 to N 0 to n minus 1. Yes, 0 to n minus 1. Yes, it varies from 0 to n minus 1. Energies of the subshells also are given. See, S subshell, lower energy than P, lower energy than D, lower energy than F. Even it tells us about the shapes of the orbitals. It also represents the orbital angular momentum, which is equal to h upon 2 pi root L into L plus 1, orbital angular momentum. Now this azimuthal quantum number tells that maximum number of electrons in a subshells SPDF, what are the maximum number of electrons? It is given by 2 bracket 2L plus 1, or you can write it as 4L plus 2. Using this formula, in S subshell, maximum how many electrons can be there? Yes, I'll show it here better. So if n is equal to 1, L values vary from 0 to n minus 1. It is 0. So yes. N is equal to 2. L values 0 and 1. It is yes and P. N is equal to 3. L values vary from 0, 1, 2. So it is yes, P, D. N is equal to 4. L values vary from 0, 1, 2, and 3. So it is yes, P, D, and F. So maximum number of electrons in these subshells can be found, and that is 4L plus 2. So what is 4? 4 into 0 plus 2. So 4 into 0 is 0. So S can have 2 electrons. 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 For P, this is for S. For P, 4 into 1 plus 2. 4 plus 1, 4 into 1 is 4, 4 plus 1, 4 plus 2 is 6 electrons. For P, it is 6 electrons. 6 electrons. For D, 4 into 2 plus 2. 4 2 is 8. 8 plus 2 is 10 electrons. For D, it is 10 electrons. D, 10 electrons. For F, 4 into 3 plus 2. 4 3 is 12. 12 2 is 14 electrons. So in the subshell, maximum how many electrons can be there? That is also being told by this azimuthal quantum numbers. So S subshell can have 2 electrons. P subshell can have 6 electrons. D subshell can have maximum. Okay, minimum it can be 1 for S subshell. Maximum is 2. Maximum. P it is 6. D it is 10. And F it is 14. Value of L for S is 0. Value of L for P is 1. Value of L for D is 2. Value of L for F is 3. Yes. So this is about azimuthal quantum number. Even it tells us the shapes of the orbit. So you can see here L values, and here. And maximum number of electrons I will write here. 2 electrons. For P it is 10 electrons. For D it is, sorry, for P it is 6 electrons. For D it is 10 electrons. And for F it is 14 electrons. Correct? 14 electrons. Right? Azimuthal quantum number is also called angular quantum number. And for a given value of n, the total values of L are always equal to n. One more point here. For a given value of n, total how many values of L you get? Total values, L values. It will be always equal to n. See here, n value is 1, total L values you have got 1. N value is 2, total L value is 2. N value 3, that means if it is the third shell, it will have 3 subshells. Understanding? If it is 10th shell, it will have 10 subshells. Yes, understanding. So for a given value of L, total L values is always equal to n. See here, this is the equation. So first one, L is equal to 0, S subshell. Second, L is equal to 0 and 1. So S has 2 electrons. Second shell 2. S and P are there. So 2 electrons maximum. And for P it is 6 electrons. Third subshell, there are third orbital, there are 3 subshells, S, P and D. For S 2 electrons, P 6 electrons and D 10. Fourth subshell, there are 4, S, P, D and F. Understanding? So this is yes, even azimuthal quantum number tells us the shape. L is equal to 0, S subshell. The shape of S orbital is spherical. Spherical. L is equal to 1, it is P orbital. The shape of P orbital is dumbbell. L is equal to 2, it is D orbital. The shape of D orbital is double dumbbell. It is double dumbbell. Then for L is equal to 3, F orbital, it is more complex. Multiple lobes are present. Shape of S orbital is spherical. Shape of P orbital is dumbbell. D orbital is double dumbbell. And F is much complicated shapes. Third one, magnetic quantum number. Yes, before that, here, principal quantum number was proposed by Bohr. Azimuthal quantum number was proposed by Sommerfeld. This person proposed azimuthal quantum number. Yeah, please do remember it. Third one is magnetic quantum number. Magnetic quantum number was being proposed by Zeeman. What does magnetic quantum number says? It tells us about the orientations of the electrons present in the subshells. Since each orientation corresponds to an orbital, therefore magnetic quantum number determines the number of orbitals present in any subshell. Number of orbitals present in any subshell. So the magnetic quantum number is denoted by the letter M or sometimes ML. And for a given value of L, it is L. What is L? Azimuthal quantum number. It has values ranging from minus L to plus L. Like how for a given value of n, L values vary from 0 to n minus 1. Like that, azimuthal quantum number is based on L. For a given values of L, m values vary from minus L to 0 to plus L. Yes, let us consider the example. So let us see the example. If n is equal to 1, L will be 0. M will be 0. Yes or no? L will be 0. Let us take it like this. N, L, subshell, shape, M. Okay. If n is equal to 1, L will be 0 because it varies from 0 to n minus 1. Correct? M varies from minus L to plus L. Okay. Subshell is called S. It is spherical. L values 0. M value 0 because minus L plus L doesn't come. If n is equal to 2, values are 0 and 1. This is S. I will same here. But if it is 1, it is P. And it is dumbbell. L values minus 1, 0, plus 1. So here I'll write number of orientations. So 0 means there is only one orientation. Correct? Here how many are there? 3 orientations. And those 3 orientations are denoted as, it is P, no? They are denoted as Px, Py, Pz. Coming to third one, 0, 1, 2. 0 and 1 I will not discuss. It is S, P, we know it. 2 means D. And the shape is double dumbbell. Correct? Values, 2, no? Minus 2, minus 1, 0, plus 1, plus 2. How many orientations? 5 orientations. 5 orientations. Which are they? Dx square, dxy, dyz, xyz are the axis, dzx, dx square, y square, and dz square. 5 orientations. 4, 0, 1, 2, I know. Third one is F. It is complex shapes, more complicated lobes, so complex. Values, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Altogether, 7 orientations. And we'll see them in our next slides. 7 orientations. Understanding? So this is how the values are dependent on each other, of the quantum numbers are dependent on each other. These three quantum numbers are the solutions of Schrödinger's wave equation. Correct? So let us see here. See the same thing what I have shown. So here extra information is given. Number of orbitals 1. Here number of orbitals 3. Orientations. This is orientations 1. Here it is for this 3 orientations 3, and here 5, and here there are 7. Yes. Orbital name. This is 1s. Second one, so 2s and 2p. This is s. So second shell 2s. Second shell, this is p, 2p. Similarly third shell 3s, 3p, 3d. Fourth shell 4s, 4p, 4d, 4f. Number of electrons 2 for s. For p it is 6. For d it is 10. For f it is 14. And number of electrons per orbital is always 2. Remember, if for per orbital the number of electrons is always 2. What does that mean? Here there are 3 orientations, right? So which are those 3 orientations? Px, Py, Pz. So Px will have, this is Px is 1 orbital, 2 electrons. Py is 1 orbital, 2 electrons. Pz is 1 orbital, 2 electrons. Similarly for D you have dxy, dyz, dzx, dx square y square, dz square. All together 10 electrons. 2 here, 2 here. So each orbital always has 2 electrons. 2 5s are 10. Understanding? So each orbital will have 2 electrons. Each orbit maximum number of electrons is given by 2n square. 2n square. Correct? Yes. Here total electrons is being given. So first shell, K shell, you can see here total electrons 2. L shell 2 plus 6 is 8. M shell 2 plus 6 plus 10 is 18. And L shell, N shell, this is N shell, this is 32. Maximum electrons are 32. And you can see here this part, what you are seeing, this part, it is about spin quantum number. Spin quantum number is associated with the electron, denoted by letter S. So what does spin quantum number says? And even these orbitals, what I said, no? So P has got 3 orbitals, right? Orientations. Orientations are nothing but orbitals, correct? So 3 orientations, Px, Py, Pz. So all will have 2 electrons, and the energies of all the 3 orientations will be same. Similarly here, dxy, dyz, dzx, dx square y square, and dz square, all will have same energies. Such orbitals having same energies are called degenerate orbitals. What they are called? Degenerate orbitals. So degenerate orbitals means what? Orbitals having same energy. They are called degenerate orbitals. And S subshell has not got any degenerate orbital. Correct? It has not got any degenerate orbital. Spin quantum number. So spin quantum number was given by Goldsmith. Goldsmith. Yes, it is denoted by S. It determines what? A spinning electron behaves like a micromagnet with definite magnetic moment. If an orbital contains two electrons, the two magnetic moments are opposite and cancel each other. So value of spin quantum number is given as plus half and minus half. Every orbital has maximum how many electrons? 2. It has 2 electrons. One electron will have spin with plus half rotating in clockwise direction, that is denoted as plus half, and another electron will have minus half rotating in anti-clockwise direction. Anti-clockwise direction. So the spin may be clockwise or it may be anti-clockwise. So this is about spin quantum number. See here. It is anti-clockwise, it is plus half, clockwise it is minus half. So this is spin quantum number. Spin quantum number. Yes. So all these quantum numbers, so we discussed principal quantum number denoted by symbol N, azimuthal quantum number L, magnetic quantum number M, spin quantum number, that is S. You can see here. So N represents the energy levels, L subshells, M orientations, S spin of the electron. Using all the quantum numbers are related to one another. Yes. So with this, let us stop the class here. In the next class, we'll be going further with the different concepts regarding the electrons present in an atom. Hope you have understood all the quantum numbers, all the theories so far. Practice them. Thank you.